that I don't think I've used with you before. And it's this, I've always had this capability, I just didn't know it. What it does is it lets me write on your paper.
Oh, that's nice.
Yeah. So, first of all, how am I going to figure out where it's increasing?
By taking the derivative.
And?
And then?
What about that? First of all, go ahead. What's the derivative?
4x to the third minus 4x.
Okay, and what is it about that that I want to know?
You want to know when it is going to equal a positive number and when it's a negative number.
When it's greater than 0 and also when it's less than 0. What's going to be the case when it's greater than 0?
Increasing.
Okay, and it's going to be decreasing when it's less than 0. So, now, how do we solve this? Think factoring. Think factoring.
We could factor out a 4x.
Okay, so now I got 4x times x squared minus 1. And can I factor that more?
No.
Well, what about the x squared minus 1? That's difference of perfect squares. So that's x minus 1 times x plus 1. With me?
Yeah.
In other words, you got to factor it fully all the way down. Okay? Now, how do we solve this problem?
So now we know the critical numbers are 1, negative 1, and 0.
Yeah, we'll go from left to right. 0, 1, and negative 1. Now what?
So then we know that there's the interval from negative infinity to 0.
The next step is draw a line chart. Okay? Here, let me redraw that because there's no need to have it confusing. There's my line chart. What points do I need to plot on there?
Negative 1, 0, and 1.
And now what do I need to do?
Now you can determine the intervals are...
How do I do that?
So you know that one of them is negative infinity to negative 1.
Well, the secret, once you've drawn the line chart, is just pick any number to the left of minus 1. As simple a one as you can find. Go ahead, pick a number to the left of minus 1.
So, minus 2?
Yeah. Now, whatever that gives us is going to apply all the way from negative infinity up to minus 1. So it's going to be really significant. So when we put in minus 2 up here, the only things we really care about are whether it's plus or minus. We don't care about the size of the numbers. So what is 4x when I substitute minus 2 in?
Negative 8.
Just negative. Like I said, I don't care about the size. What is x minus 1 when I put in minus 2?
Minus.
And what is x plus 1 when I put in minus 2?
Minus.
So am I negative or plus to the left of minus 1?
Negative.
Right, because I got 3 negatives make a negative. So these are all negative. Now, usually these alternate. So the next interval would be plus, the next interval would be minus, and the next interval would be plus. And I actually had a student once that told me their teacher told them that they would always alternate. And if you had no more time to do the problem, in other words, test time was over and you had to put your answer down in 30 seconds, that's what I would do. I would call this plus, this minus, and this plus. And then you would have your answer, right? But I have found some functions that do not alternate. So it's not particularly safe to assume that they alternate. So let's do the next interval. What number should you pick?
We could do -1/2.
Okay, what's 4x?
Negative.
What's x minus 1?
Negative.
And what's x plus 1?
Positive.
So that is positive there in that entire interval. In other words, all you have to do is check one number in that interval, and whatever it gives you applies through that whole interval. Now, let's try positive 1/2. It's 4x.
Positive.
It's x minus 1.
Negative.
And x plus 1.
Positive.
So that's negative in that interval. And finally, pick a number greater than 1.
2.
And you get positive, positive, positive. But like I said, 90% of the times, once you figure out the first interval, you know all the others. They just alternate. But I have run into problems that don't. So don't use that unless you're in an emergency. So what is, do you have to give this an interval notation?
Yeah.
Okay, so increasing on what interval?
So it would be -1 to 0 and 1 to infinity.
And parentheses or brackets?
Parentheses.
And decreasing?
-infinity to -1 and 0 to 1.
Again, parentheses around everything. Always have parentheses around infinity, and you have parentheses around the number if it can't actually be that number. And it can't actually be 0, because if you make x 0, then it's not greater than or less than 0. It's equal to 0. And what you need is for these to all be, that's the positives, that's the negatives. We do not allow for equal to 0. Okay. All right, let's look at this other one. Okay, what's our first step always?
Take the first derivative.
Yeah, I'm going to do that up here. Just give myself some working space. What is it?
Cosine of x times negative sine of x. Well,
Hold on, I always get confused when people use the product rule because I never know which way they're going. So I tell you what, give me the entire answer. However you do it, what is the derivative of sine x times cosine x?
Okay, so the derivative of sine, which is cosine, times sine.
Hold it. Times cosine, right?
Right.
In other words, if we're going, this is kind of, I don't know if I do this for the student's sake or my sake, but it's I think useful to always do these the same way. In other words, the product rule is u v prime plus u prime v, right?
Mm-hmm.
Well, I can do that in either order since it's addition. And so when I ask a student to do this, I never know which one they're doing first. I don't know if they're doing this one or this one. So it can be a little confusing. And perhaps there's something to be said for always doing it the same way. In other words, let's always take the derivative of that first term. Well, if we're taking the derivative of the sine x, then it's being multiplied by the cosine x. Now, what's the rest of it?
Plus sine x times negative sine x.
Which is minus instead of plus. In other words, it changes that to a minus sign. And notice that that is cosine squared x minus sine squared x, which actually is the identity for cosine of 2x, although I don't know that that's what we want to do here. It's just, so far, that's f prime of x. Now, we want to find out where that is increasing and where it's decreasing. So where is that greater than 0? You know what? Let me think about this for a second, but using that identity might be the easiest thing to do. Trying to figure out how else I'm going to do this. I could factor. In other words, I'm looking at difference of perfect squares, so it's cosine x minus sine x times cosine x plus sine x. Not sure how to figure the critical numbers if I do that. I guess they would be pi over 4 for the cosine x minus sine x, and the cosine x plus sine x would be 0 would be the only critical number. You know what I'm saying?
Mm-hmm.
I'm not sure that's the best way to do it, though. In other words, let's talk about doing it that way. I can call it, oops, hold on. I can say it's difference of perfect squares, and I got cosine x times sine x all times cosine x plus sine x. And that's what has to be greater than the 0. Well, if I look for my critical numbers, it's where that's 0 or that's 0, correct?
Yeah.
Problem is that it's 0 when it's 45 degrees. So my critical points, do you care if it's in radians or degrees? Yeah, they gave you the interval 0 to 2 pi. So let's use radians. So when x is pi over 4, I know I got square root of 2 over 2 minus square root of 2 over 2. So it makes that 0. Now, when I go in my second quadrant, this might work. I'm not sure it's going to be the fastest way, but might be. What's my other critical point? In other words, what other quadrant is the sine of cosine the same as the sine of sine?
Would it be 5 pi over 4?
Yeah, the third quadrant. In other words, it's the third quadrant angle that's the equivalent of pi over 4. And that's it. The first and the third is the only ones that produce critical points in our unit circle. Now, let's look at this one. What makes that a critical point? Well, it's whenever, it's not when x is 0. That's 1. It's the other two quadrants for pi over 4. You see why?
Yeah.
In other words, it's got to be at 3 pi over 4. I know the answer is root 2 over 2, but one of them's positive and one of them's negative because they have different signs in the second quadrant. When I say different signs, I mean SIGN. Well, the other place where they have different plus or minus signs is the fourth quadrant. Cosine's positive, sine's negative. So that angle also, 7 pi over 4. So those are the 4 critical points. Okay? And again, I'm going to label those and merely test left and right of them. And I'm going to put them in order. I bet they alternate. And then we're going to use the same tactic we used before. Since I've got the critical points down here, I'm going to erase them from here so that I got room to write. What's a good value to start with for testing?
Could you test 0?
Perfect. What's cosine of 0 minus sine of 0? Is that a plus or a minus?
Plus.
It's cosine of 0 plus sine of 0.
Also plus.
So that region is that. Now what's a good number between pi over 4 and 3 pi over 4?
Pi over 2.
Good. What's cosine of pi over 2 minus sine of pi over 2?
Minus.
And what's cosine of pi over 2 plus sine of pi over 2?
Plus.
So that region is negative. And let's try pi in between 3 pi over 4 and 5 pi over 4. And we can assume that if this comes out plus, then the rest has to alternate, especially since we're talking about sines and cosines. Talk about an alternating function. In other words, I don't think there's any way sines and cosines can have two intervals together that are the same plus or minus sign here. But let's just check. I might be wrong. So cosine of pi is what?
Is negative 1.
Okay, and what's the sine of pi?
0.
So that's negative. And cosine of pi is negative also. So that is positive. And at this point, just fill it out and take your chances. And I say that with a little bit of just, but not a lot. In other words, there's always a fine line on how much work you need to do on these before you figure out the answer. Okay. Now, what is the answer? Where is it increasing?
Negative infinity.
No. That's why I asked. It was a trick question. What's the domain that they've given us?
Oh, so it's 0 to pi over 4.
Correct. So 0 to pi over 4 in conjunction with 3 pi over 4 to 5 pi over 4 in conjunction with, what's the last one?
7 pi over 4 to 2 pi.
Okay. Now, it's interesting as to whether or not I need a parentheses or a bracket.
Mm-hmm.
I think you need a bracket at 0.
Yeah.
Because at 0, we're increasing, right?
Mm-hmm.
I think, let's see, when I plugged in 0, I got a positive there, and I got a positive there. So at 0, this function is increasing. Let me just draw, in other words, this has to be a bracket right there, not a parentheses. And it has to be a bracket there. It's also continuing to increase at 2 pi. That's the same as 0.
Mm-hmm.
Now, it's not increasing at 3 pi over 4. It's neither increasing nor decreasing. Excuse me, at pi over 4. So I need a parentheses there, and I need the union thing in between these also. Do you understand why we need brackets at 0 and 2 pi?
Yeah.
Okay. Because the function is doing that, and they've asked us to restrict the domain to 0 to 2 pi, and at 0 it happens to be increasing. So that's definitely bracket. It's increasing at 0. Usually you draw your limits there, right?
Right.
In other words, where it stops increasing. And at that point where I've put the x, it's neither increasing nor decreasing. So that would always be a parentheses around that point. Same thing down here. It's neither increasing nor decreasing. But at the beginning of our interval, 0, it was actually in the middle of its increasing cycle. Same way as we approach 2 pi. 2 pi is somewhere like right there. We're in the middle of increasing. Now, decreasing, decreasing is not the same, is it? What's the answer for decreasing?
Pi over 4.
Parentheses or bracket?
I think it would be parentheses.
Correct. At pi over 4, we are neither increasing nor decreasing.
Mm-hmm.
To what?
To 3 pi over 4.
Parentheses or bracket?
Parentheses.
In union with?
5 pi over 4 to 7 pi over 4. With parentheses.
I'll bet you most people will get this problem wrong. They'll lose points because they put parentheses around the 0 and the 2 pi. It's a very odd situation when you're listing intervals of increasing and decreasing to ever have brackets.
Yeah.
Okay, very unusual. The only reason we do here is because they made an interval that was in the middle of where we were increasing on both left hand and the right hand side. We're still increasing at 0 and at 2 pi. Mm-hmm. So that's why you got to have a bracket, but that's an unusual requirement that they put there. In other words, it would have been more typical had they not restricted the domain and then you would have been correct. Well, not really. It wouldn't have been minus infinity to pi over 4. It would have been minus pi over 4 to pi over 4.
Mm-hmm.
And so forth and so on. In fact, it would have been very difficult to even describe. We would have had to use infinite sum notation. Well, do you know what I mean by infinite sum notation? In other words, if I say my answer is pi over 2 plus n times 2 pi, are you familiar with that notation?
No.
No? Okay, I won't even talk about it then. It's yeah, it's when your domain is not restricted. That's the kind of notation you have to use. What did I do? I closed out my... Did you send me just one picture, or was that the only one?
I think there were 3.
Okay. Sorry, I closed it out accidentally.
No, that's okay.
Oh, actually, we still have this to do. Okay. Here, I think I'm going to do this one on my sheet.
Okay.
I don't know why, I'm just feel a little more comfortable with mine. And I can just blow this up like that. So I want to, I'm sorry, now I got to reread the title. Use the first derivative test to find the relative extrema. Okay. First of all, oh man. What's first step?
Take the first derivative.
Yeah, always. That's the answer to every single calculus question that says what's the first step. At least when you're taking differential calculus. When you get to integral calculus, then the first step might be take the integral of it. But not always. A lot of times when you take the integral, the first step is take the derivative, believe it or not. So let me think, is there an easy way to do this? Don't see it. All right, tell me what the first derivative is. Do it step by step and then we'll simplify it.
Okay, so x squared minus 9 times 2x minus x squared times 2x over x squared minus 9 quantity squared.
Okay. Now, where are local extrema going to be? That's what it wants. It wants us to use the first derivative test, which is fine, better than having to take the derivative of this thing. So what are we looking for the first derivative to be? What are what would be called critical points?
Well, definitely plus or minus 3.
Okay, in other words, wherever the denominator is 0, that's going to be a place where the first derivative is not defined. Okay, so it can be not defined. That's probably not going to be a relative extrema now that I think about it. If your first derivative isn't defined, then it's got to have a vertical asymptote, and it might look hyperbolic in nature, and it's not going to be a relative extrema. At least I don't think. what's the other place? What's the most common place we look for extrema?
When the numerator equals 0.
Well, when the first derivative equals 0. And that happens only when the numerator is 0. In other words, we don't really care what the denominator is, although if the numerator is 0 and the denominator is 0, then now we know we got problems. That's a limit problem, right?
Yeah.
Let's figure out what this numerator is. In other words, the only way we can do that is to multiply it out and see if everything goes away. What do we got? We got 2x cubed minus 18x minus 2x cubed. So the x cubes did go away. And the only, did I do that right? Yeah. Yeah, the only place where this thing is 0 is at x equals 0. So I'm going to say that that's the only place where I have a minimum or a maximum. Knowing, if you look at this function, this is hyperbolic in nature, okay? But it's hyperbolic in the sense that there's two vertical asymptotes at plus or minus 3. We know what these things do, and then there's a horizontal asymptote at y equal 1. Well, hyperbolic means it's going to look something like this. Well, there's no extrema in that picture.
Yeah.
The other way it could look is if that red line doesn't go all the way up and it turns around and comes back down like that, and then that usually looks like that. So that's the other picture. And that appears to be the picture we're looking at, right? In other words, doesn't it have to be? If it was my first red graph, I would not have found a horizontal tangent line. In other words, let me go back here. I don't want to confuse you, but this is actually a pretty good point. If the graph looks like this, notice there is nowhere in that thing where there is a horizontal tangent line, which means it would be impossible for the first derivative to produce a 0. And yet we produced one. That very clearly tells me that there has to be somewhere where there's a horizontal tangent line, and in fact I know that it's right at 0. It's got to be right there. And then they almost always come on the other side of the asymptote from the opposite infinity. So I'm pretty clear in my head that this is the picture I'm looking at. Okay? But the question said, use the first derivative test to prove whether we're looking at a maximum or a minimum, correct? Use the first derivative test to find the relative extrema. Well, we did that. And then say where there's a relative maximum or a relative minimum if there is one. Well, we know that it's at x equals 0, but we didn't really use the, yeah, I guess we did use the first derivative test. Although not really. Not really. Without graphing it, and the only reason I knew how to graph that is because I'm very familiar with hyperbolic functions, okay? I mean, I do it all the time. But if I didn't graph it, just by setting y prime equal to 0 and discovering that we have an extrema at x equals 0 doesn't tell us whether it's a maximum or a minimum. Now I can see that it's a maximum from my graph, but how do we use the first derivative test to tell that it's a maximum, not a minimum? Here's the first derivative test. You have to test the slopes to the left of your critical point, which is 0, and you have to test the slopes to the right of that point. The reason is that my slopes in my picture go plus, 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 0, minus, 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 minus. So when the slopes, or the first derivatives, go from plus to minus, that makes it a local maximum. If I had something like this, the slopes are going minus, 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 0, plus, plus, plus. So if the slopes go from minus to plus, you're dealing with a minimum. Well, how do we figure out here? It's not that tough because our y prime came out to be a relatively simple number. So what are the slopes to the left of x equals 0 going to be? Positive or negative? Positive, exactly. And what are the slopes to the right of 0 going to be?
Negative.
So this picture fits perfect. And we're dealing with a maximum at 0. Now, this is our original function, not the derivative. And I can tell that my original function is not defined at minus 3 or plus 3. And if the function is not defined at those two values, then the first derivative is not defined at those two values either. And in fact, yeah, I screwed up here, although not really. Minus 18x is not our first derivative. It's minus 18x over x squared minus 9 squared, right?
Right.
I forgot about that, but you can't forget about that. If I'm applying the first derivative test, I got to do it to that. Now, the fact of the matter is that this denominator is always positive because it's something being squared. So since the denominator is always positive, I can effectively ignore it and work only with my numerator to the left and to the right of x equals 0. Okay, so I made a mistake, but upon second looking of it, I would have done it exactly the same way. I just didn't want you to think our first derivative was minus 18x. It's not. It's that divided by that. And notice that our first derivative is still not defined at plus or minus 3. So if I were to graph the first derivative function, it would also be hyperbolic in nature with these same two vertical asymptotes, oddly enough, which is kind of interesting. Who knew when you could go from a function to its derivative and end up with the same two vertical asymptotes? So I think we've answered the question, and not only that, there is no relative minimum, right? In other words, if I look at that graph, if that's the correct graph, there's no relative minimum anywhere. You certainly cannot call the horizontal asymptote a relative minimum because it never reaches it. It goes on and on to infinity, always getting closer and closer to it. So what number would you put on it as a minimum if I was going to call those the minimums? But the fact of the matter is that there is no first derivative that goes from negative slopes to positive slopes. And that's what you need for it to be a minimum. All right, guess we finished that problem, 6. So let me close that out. Don't tell me I did it again. Boy, it would be nice if I knew how to use my operating system. Sorry. I Oh, I bet I'm clicking on the wrong X. Yeah, I'm thinking I'm clicking on the inside X and I'm clicking on the outside X, closing out my whole Gmail thing.
I hate it when that happens.
Yeah, all right. So I want to go down to the next one. This one here, right? Is that middle page skippable, or is there something on there that I need? I can rotate it if I can download it. Question is, can I download it? Let's see if I click on it. It doesn't let me rotate it. Oh, download. I'll download it. And now, if I open that file, I should be able to rotate it. There we go. Oh, these were actually the first 3 problems, it looks like.
Yeah.
Doesn't matter, I guess, huh?
No.
Okay. Let me blow that up a little bit. And then do my thing. And now I can write on this thing. First of all, notice the denominator. Never 0. Whenever you have something squared plus a number, always positive. So there's no horizontal or there's no vertical asymptote on this thing. Well, give me the first derivative.
So it would be x squared plus 1 times 2 minus 2x times 2x over x squared plus 1 squared.
Which I think we're going to basically be able to ignore that denominator. Let's see, we get 2x squared minus 4x squared. So we have a minus 2x squared plus 2. And then, oh, I remember. Did we do this problem once before? I've done it with somebody because I remember I almost made the same mistake last time. It looked like I could factor out a 2, leaving behind an x squared plus 1. But you can't. If I factor out a minus 2, I leave behind an x squared minus 1.
Oh.
Okay? But it looks like that could be simplified, that whole thing. And it really can't be. X squared minus 1 over x squared plus 1 does nothing. Can't do anything with it. However, we're back to only worrying about the numerator. So we want to know where that's 0. Well, where is that 0? So x squared has to be equal to 1. What's x equal to?
Plus or minus 1.
Good. So those are 2 potential extrema. Within the interval. Now, because they say find the absolute extrema, what am I going to do other than examine these 2 points?
You also look at the interval.
The end points. Because what if my function goes like this on that interval? Well, there's an extrema, but neither one of them is an absolute. If my interval goes from here to here, then I've got to not only find the y value at my relative extrema, but I got to compare those two values with that value and that value. Then I'll know whether I'm looking at an absolute extrema. Okay. So, what is, and we are, yeah, okay, what's the next step?
So then
we need 4 values. I need to figure out which of these values is the biggest, which one of them is the smallest. We need f of 1, we need f of minus 1, we need f of 2, and we need f of minus 2. Those are the endpoints. What's f of 1? And we're not dealing in the derivative function here. We want to know where the absolute maximum and minimum are in this function, the original function. So what's f of 1?
So it would be 2 over 2, which is 1.
What's f of negative 1?
Negative 1.
What's f of 2?
4/5.
And what's f of negative 2?
Negative 4/5.
Where are my absolute extrema?
1 and negative 1.
Correct. And that's clearly the minimum, that's clearly the maximum on that interval. And that's the way you have to do those absolute extrema, is you got to check your relative extrema and your endpoints and just compare all 4 values. And whatever the smallest value is, that's your absolute minimum. Whatever the biggest value is, that's your absolute maximum. Okay, let's look at the second one. What's that whole question say? Find the points guaranteed by the mean value theorem for f of x equals root x plus 2 plus x, and then just c equals. Oh, on the interval, is that the rest of it? On the interval 2 to 7?
Yeah.
Okay. All right. What they're talking about here is, I don't know what that function looks like, but let's assume that it looks like this. Okay? There's 2, there's 7. What the mean value theorem says is that whatever the average slope between that point and that point is, there is going to be a point between 2 and 7 that we will call C, where the slope of the tangent line is the same value as that average slope. That's what the mean value theorem says, is that if you have a continuous function, there has to be a point in between the beginning point and the ending point whose derivative is the same value as the average value. And what that means is that, well, let's talk about the average value. what's the average value between 2 and 7 of this function? And let's talk about it in general terms. It's f of 7 minus f of 2. See why? That's f of 2. That's f of 7. And I want rise over run. Well, f of 7 minus f of 2 is the rise, and the run is 7 minus 2. So that is my average rate of change between 2 and 7. And I can figure that out. Let's see. Oh, we're down here. Let's see. When I got 7 in there, it is 3 plus 7. So that's f of 7. When I put 2 in there, I get 2 plus 2, 4. And 7 minus 2 is 5, so I've got 6/5. So 6/5 is the slope of that line that connects the points f of 2 to f of 7. Now I got to find c. What do I need to find? I need to find the first derivative of this function where the slope is equal to 6/5, right? Okay, well, what's f prime of x? Hold on a second. Let me just figure out what I can erase here. I can erase some of this stuff here. Don't think I need this thing here anymore. I'm going to leave that picture. And we know that that slope is 6/5. Okay? And I know this slope right there also is 6/5. I just don't know where it is. In other words, I don't yet know what value of c is going to give me a slope of 6/5. But it's pretty easy. I'll take the first derivative of this, set it equal to 6/5, and solve for that value for c. Well, what's f prime of x for the bottom one?
So it would be 1/2 times x plus 2 to the negative 1/2 plus 1.
Okay. And that quantity is what I want to equal 6/5. Because remember what first derivatives are. Slope. It's the slope of the tangent line. Well, I'm looking for a tangent line that has a slope of 6/5. Well, my slope of the tangent line is always this function. So now all I got to do is solve that function. Well, that shouldn't be that hard. Let me write it in a little bit simpler manner. I'm going to move the 1 over. Now it's going to equal 1/5. With me?
Mm-hmm.
Well, both numerators are 1. That means both denominators have to be equal. So I've got the square root of x plus 2 equals 5. Square both sides. X plus 2 equals 25. X equals 23. Wonderful. How do we get a value that's not in the interval? I'm trying to figure out my mistake. I've got a mistake somewhere in here. Let's see. I know that the method is correct. Our derivative is 1/2 of x plus 2 to the minus 1/2 plus 1. And that derivative has to be equal to 6/5. Which means this part of it has to be equal to 1/5. Because I'm going to subtract 1 from 6/5. I got a 2 over here I didn't do anything with. In other words, there was a 2 there that I forgot to write. Okay? So now it's 2 root x plus 2 equals 5. You with me?
Mm-hmm.
Sorry, I hate to make mistakes like this. And that's going to actually make a big difference, believe it or not, the absence of one little old 2, because now when I square both sides, I get 4 times x plus 2 equals 25. And now x plus 2 equals 6 1/4. And x equals 4 1/4. Thank goodness it's between 2 and 7. 4 1/4 is the value for C, where the derivative at 4 1/4 is the same slope as it is between 2 and 7. That's what the mean value theorem says. So whenever they're asking you to find the C for the mean value theorem, that's what you got to do, is you got to take the derivative of the function and compare it with the average slope between these 2 points, between 2 and 7. And you get the average slope by f of 7 minus f of 2, all divided by 7 minus 2. All right. And that was the last. Ooh, that's interesting. Oh, that's because now I don't want to make the same mistake I keep making. Okay, now I think I'm all right here. Yeah, I still have, I can close that out, and I can scroll down to the next page, or just do that. Is this where we want to be? What do we got? 1 minute? Is it really 6:59?
Oh, I didn't even know.
Part of the problem, when I use that other program, it takes a picture of my screen and lets me write on that, but it freezes the clock. And so
Oh, no.
I was in a session yesterday, and it was like 5:47, and boy, after 5 minutes passed, it was still 5:47. I couldn't figure out what was going on. So I guess this is a good place to stop, huh?
Yeah.
Especially since I have a 7 o'clock I got to go to. But anyway, hopefully that was helpful. I'm sorry we didn't get to cover all the problems, but some of these were fairly tough.
Yeah.
But that should have been helpful.
Yes.
All right. All right, Brianna. Talk to you next time.
You too. Have a good night.
Bye-bye.